Welcome back. Please check your answers to the horizontal asymptote practice. The 4 answers are here. And we're going to review what we've been working on this week with just 2 sample problems. The first of which is written here. And as we've been doing forever, we're going to start by factoring. Denominator is already nicely factored. This is just an x squared. So we need 2 numbers that multiply out to -12, add up to -1, and it's looking like -4, +3 will do it. When we started factoring these rational functions, we always stated the excluded values, and we would have to here exclude x equals 4, because that makes the function undefined. Can't have a 0 in the denominator. We do not have a value when x equals 4. Yeah, kind of squeeze that undefined on there. Alrighty, so we want to be able to find the x-intercepts, y-intercepts, and these two will probably do together. The vertical asymptote, any holes in the graph, and finally the horizontal asymptote. And I hope I saved enough space. So the x-intercept, that's anything that makes the numerator 0, but not the denominator. Because we can't have the denominator being 0. Okay, so if we look at our numerator here, the numerator is going to equal 0 if x equals 4, or x equals -3. Well, we have already excluded x equals 4, so that cannot be an x-intercept. Our x-intercept can only be the point -3, 0. So we have an x-intercept. Y-intercept, well, that happens when x is 0. So if we put 0 in for all of these x's, we get, well, I'm just going to put 0 in the original one. We get 0 minus 0 minus 12 over 0 minus 4, which turns out to be 3. So our y-intercept is 0, 3. Oh, great, we got 2 points. We know about this graph. Okay, vertical asymptotes, holes in the graph. We look at the denominator. If we have a factor that cancels out, it might be a hole in the graph. If we have a factor that does not cancel out, it may represent an x value that is going to make a major break in the graph of vertical asymptote. So we have x minus 4. Whoa. And the x minus 4s cancel out, which means we may have a hole in the graph at x equals 4. Now, I'll come back to that in just a moment. When we cancel out the x minus 4s, we just have x plus 3 over 1, which is x plus 3. There's no vertical asymptote here, which I was supposed to put in a different color. Because once we canceled out that x minus 4, we don't have any values that make the denominator equal 0. So there's no vertical asymptote for this particular function. But there is a hole in the graph at x equals 4, because that makes the denominator equal 0, but it canceled out. So it's not a major break, it's just a single point that's missing. We need to find the y value. And we're going to get the y value by putting x equals 4 into the reduced fraction. So the reduced form is just x plus 3. When x equals 4, y equals 7. So we have a hole in the graph at the point, just a single point, 4, 7. Okay, horizontal asymptotes. In the last video, we talked about those being comparing the degree. If we have a polynomial over a polynomial, all we have to do is compare the degrees, and we'll be able to tell whether there's no horizontal asymptote, or it's going to equal y equals 0, or it's going to be the ratio of the leading coefficients. Well, the numerator degree in this case is 2. The denominator degree is 1. And if the numerator has a higher degree, that means that the fraction just keeps getting bigger and bigger and bigger, so there is no horizontal asymptote. If, and we're not going to be asked to do this in this class, but if we were asked to do the graph, we know it has an x-intercept at -3, 0, a y-intercept at 0, 3, and we know that at the point 4, 7, which I'm going to guess is sort of around here, there's a hole in the graph. And that was totally off the sheet. I apologize. I wasn't paying attention. So we'd have the x-intercept here, the y-intercept here, a hole in the graph at the point 4, 7, and the rest of the graph's just a straight line. Look at just one more example. If f of x was this rational function, as usual, first thing we're going to do is factor. And I'm sure you all know by now that this is the difference of two perfect squares up here. This is actually a perfect trinomial square, but so we need two numbers that multiply out to 25, add up to 10. And because this is a fraction, we have to worry about any numbers that make the denominator equal 0. So we are going to exclude x equals -5 because the function is going to be undefined at x equals -5. Once again, we're going to go after the basic parts. X-intercept, excuse me, y-intercept, considering both at the same time, the vertical asymptotes, holes in the graph, there can be more than one hole in a graph. And finally, the horizontal asymptotes, of which there could be two. Okay, so x-intercept would be anything that makes the numerator equal 0. So that would be x plus 5 times x minus 5. It's got to come out to 0. Well, our choices are x equals -5 or x equals 5. Those are our candidates for x-intercept. However, we have already found that we can't use the value x equals -5. We are going to have to exclude that value, and our only x-intercept could possibly be when x equals +5. So the x-intercept is going to be the 0.50. We have to leave out the -5 because that makes the denominator equal 0. Y-intercept, when x is 0. I'm going to put that back in the original function. We'd have 0 minus 25 over 0 plus 0 plus 25. So that just comes out to -1, which makes the y-intercept the 0.0, -1. Okay, moving on. Vertical asymptotes, holes in the graph. We're going to worry about the denominator here. I'm just going to recopy the factored form. Now, if the factor that makes the denominator equal 0 cancels out, that usually means there's a hole in the graph. There may be a hole there. If the factor does not cancel out, then we're going to have a vertical asymptote. Okay, we have an x plus 5 in the numerator, which will cancel with either this x plus 5 or that x plus 5, not both of them. So I'm just going to go straight down. Technically, that's just a 1. Alrighty. So even though this factor of x plus 5 canceled out, we still have a factor of x plus 5 in the denominator. So this is not going to be a hole in the graph because it canceled out once, but it's still sitting there. So we have a vertical asymptote because that x plus 5 did not cancel out. And the vertical asymptotes are lines, so it's going to be x equals -5 because that's what would make the denominator equal 0 here, but it would not make the numerator equal 0. And there are no holes in the graph. Finally, for the horizontal asymptote, we just compare the degrees. And I would look at the original. So the numerator has the numerator degree is a 2. The denominator degree is also a 2. And if they have the same degree, we just write the ratio of the leading coefficients. So the horizontal asymptote is going to be 1 over 1, or we write the equation, horizontal line is going to be y equals 1. Now we were not asked to graph this, but if we were, we do know some things about the graph. We do know that it's got an x-intercept at 5, 0. It has a y-intercept at 0, -1. It has a vertical asymptote at x equals -5, and the graph cannot cross the vertical asymptote. It has a horizontal asymptote at y equals 1. And it can cross the horizontal asymptote if it wants to. The graph ends up actually looking something like this. Excuse me. You're not expected to produce the graphs at this point, but hopefully you'll be able to recognize the various features that we have figured out as we work through the problem. So now it's your turn. You have one example, and you can use its graph to check it. And then please move on to the review. And there is a quick quiz on the unit from this week. If you have questions, please contact your teachers.